with Alex Becker, and today we're going to discuss this paper from MIT, which is titled 6D Self Localization of Drones Using a Single Millimeter Wave Backscatter Anchor. And let me just read the abstract and then I will turn it over to Alex for a short presentation on this paper. So, the abstract is as follows. We present the design, implementation, and evaluation of MiFly, a self-localization system for autonomous drones that works across indoor and outdoor environments, including low visibility, dark, and GPS-denied settings. MiFly performs 6 degrees of freedom self-localization by leveraging a single millimeter wave anchor in its vicinity, even if that anchor is visually occluded. MyFly core contribution is in its joint design of a millimeter wave anchor and localization algorithm. The low power anchor features a novel dual polarization, dual modulation architecture, which enables a single shot 3D localization. Millimeter wave radars mounted on a drone perform 3D localization relative to the anchor and fuse this data with the drone's internal inertial measurement unit, IMU, to estimate its 6 DOF trajectory. We implemented and evaluated MyFly on DJI drone. We collected over 6,600 localization estimates across different trajectory patterns and demonstrate a median localization error of 7 centimeters and a 90th percentile less than 15 centimeters even in low light conditions when the anchor is fully occluded visually from the drone. And there is a link to the demo video. Alex, I'm turning it over to you. Please, I'm going to share the presentation now, and please take it away, but present yourself first so the people will know your name. 1 second, I'm going to stop sharing, and then I'm going to share my screen again. And now I'm going to share the presentation. Second. Okay. Let me know if you can see it, Alex.
Uh, yes, I can see it. So first of all, hello, my name is Alex Baker. I'm a radar engineer. Worked in several companies developing different radars in different technologies and frequency bands. I have a second degree from Ben Gurion University in Israel. And I'm also the author of Kalman Filter from the Ground Up book, explaining Kalman filter for beginners and based on numerical examples. Uh, so let's start with the presentation. Short overview. We can go to the next slide. Neil.
Yep. I'm turning it.
Okay. Uh, Actually, what we have here is a very nice idea from MIT using radar for drone location. They talk about indoor, but it also could be outdoor location also in scenarios where GPS is not available. There are several technologies for drone self localization. First of all, the GPS, but GPS it's not available indoor and it can be jumped outdoor. IMU localization it suffers from bias. Vision-based approaches they need good light conditions. LiDAR need uh, some features in environment that can't perform good according to this paper in uh, in the rooms with plain walls. And the ultra wideband ranging system require multiple anchors in the buildings, and they work on trilateration. principle.
Mhm.
Let's go to the next slide. There are two papers that were published about these projects. Here are the links, and let's continue. Here we talk about selection of the frequency band.
Mhm.
Uh, the low frequency system, they are best for non-line of sight conditions and penetration through walls and
Mhm.
propagations and high range, but they have a very low angular resolution, and they need big antennas because of relatively big wavelengths.
Mhm.
Going to high frequency systems like 60 giga and 77 giga, it's much better resolution, but it's shorter range, high power consumption, and it's usually expensive systems. So they selected the 24 gigahertz frequency,
Mhm.
and I also have experience with working with models in these frequency bands. It's falls within ISM band. It's commercial available and it's quite cheap.
Mhm.
It's low power and it doesn't require large antenna.
Mhm.
Uh, let's go to the next slide. They used Infineon position to go radar. It includes complete radar. That means the RF part and also the digital part, including microcontroller. And usually these modules come with the signal processing implemented inside, so you actually get the measurements. Or sometimes you can make your own signal processing on on their chip, on their microcontroller.
Alex,
We can see that
question. This radar, I don't remember. This radar is also measuring Doppler or no?
it can, it can, yes, it measures Doppler. I didn't include it here in the presentation because MIT doesn't use Doppler.
Mhm.
Uh, for in their project, they only measure the range.
Mhm.
Okay.
Yep.
The detection distance is less than 15 meters, and I must say that probably, I don't know, I didn't find information on this chip.
Mhm.
It lacks LNA
Mm.
because in other solutions in this frequency band, you can get much higher ranges. Uh, Usually they use these chips for proximity sensor or collision avoidance sensors, and short distance is enough.
Mhm.
The range resolution is 0.9 meter, and angular accuracy is it depends on antenna. It's below 10 degree or below 5 degrees.
Mhm. Good.
Let's go to the next slide.
Mhm.
I'll jump ahead, and I will say that MIT claim that they reach the range resolution of single centimeters, but in 24 gigahertz ISM band, uh, if you take the full bandwidth, which is 250 megahertz, so you can reach the range resolution of 0.6 meters. You can do additional signal processing to get it down, but reaching, for example, accuracy of 1 centimeter without any external aid like IMU, it's very challenging. And in their paper, they didn't explain how did they reach this accuracy in positioning.
No.
And if you divide this frequency band to several frequencies, For example, you one use for vertical polarization and another for horizontal polarization, then you have less than 250 megahertz. And if you have several drones in the building or in the area, and you want to avoid the interference, so you must divide it somehow in frequency or in time. Um,
Yeah.
and if you divide it in frequency, so you get again much less frequency resolution.
Yeah. Yeah. Even though
Okay,
for one drone, it's not necessary to divide. They didn't
uh,
divide,
th-
I think.
they divided. You take a look on the picture here. They use two models. One for with horizontal polarization and
Hmm.
one with vertical polarization
Hmm.
to measure elevation and azimuth
Right.
each. Okay, so
Right.
they divided it also in frequency because of the leakage between cross polarization. It's usually about 20-25 dB,
No, no,
and
that's not what they
hmm?
did, Alex. That's not what I understood. I understood that the transponder that they have, which is it's the novel part of this work is transmitting to the it's taking the signal and it's moving it in a carrier. So it's basically shifting the peak a little bit,
Mhm,
and it's shifting with different frequencies for the vertical and the horizontal polarization. So they still use this 250 mega, just
uh-huh.
the peaks are
Okay,
shifted differently.
okay,
The-
okay.
It's a nice idea. It's a nice
Yes,
idea.
yes,
Yeah.
definitely. Okay. So actually, they put two models on the drone. Usually, these models they can they measure only azimuth angle.
Hmm.
So if you want, I didn't find. I tried to search web, but I didn't find any model that can use both azimuth and elevation. So
Hmm.
they put two models together
Hmm.
on the drone. And by measuring range, azimuth, and elevation, I actually have XYZ coordinates
Hmm.
after transformation from spherical coordinates to Cartesian. And uh, the anchor, you can use a single anchor in the building or in the area. You must point always your antenna towards the anchor.
Yeah.
They use IMU to detect rotation.
Hmm.
So when a drone rotates an angle, so the azimuth, for example, angle changes,
Yeah.
but the
Yeah.
position doesn't change. So they use IMU to detect this rotation.
Yeah.
Uh, let's go. This way they have 6 degrees of positioning, 6 degrees of freedom positioning using IMU. And the performance is very impressive. The report of median errors of below 5 centimeters in X, Y, and Z positions.
Hmm.
And they also report good positioning in non line of sight conditions. Um, but they didn't provide any description of this non-line of sight scenario, which kind of
Right.
wall, on which kind of obstacle, etc.
Yeah. 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 They didn't. They said it was occluded, but they didn't specify what was the occlusion.
Yes.
Right. Also, I have some, you know, I have a question here.
Hmm.
They report median error, and for me it's a small red flag because it means that the mean error is larger because of outliers, maybe.
Yes. Yes.
Otherwise, why
Probably.
why take the median? And and that means
Yes, they also didn't specify standard deviation of the
no,
error.
no, they specify the 10th and the 90th, I think, percentiles, but they didn't specify standard deviation or variance, and they didn't show the distribution. So
Hmm.
I my thought is that this distribution is somehow maybe bimodal or skewed or something like that. I don't know. I'm just thinking out loud.
Yes,
Uh,
but this is still nice idea. This is academic project,
yeah,
and if you want to use it commercially, so there is still a lot of work to do on this
yes,
idea.
yeah, definitely, definitely. Yeah, the anchor idea is the anchor is basically a transponder. So it's the idea is not novel because they have I guess two ways of differentiating. One is shifting the polarization, right? So that the
Hmm.
polarization there will be a polarization attenuation when vertical meets horizontal and vice versa. And second, they shift by different frequencies the horizontal and the and the let me switch back to the actual paper. Yeah.
Hmm.
Okay. And you can see here that in the paper they show there it is. There it is. They show it. You see, this is the desired signal, and you see that in baseband you see it in 350 kilohertz, and this is the leakage signal. Now the shift between them is determined by the shift that they determine between them. They
Hmm.
are shifting the horizontal, let's say by 300 kilohertz, and the vertical by 350 kilohertz. So there is a shift between them, and thus they can not only look at the peaks and understand what's going on there because they have this space between them. uh, I think they can also take more averages here or weighted averages to reduce the or to better the accuracy, if you will. And it's diversity. So they have diversity in polarization and in frequency, and maybe
Yes.
that's why they are able to lower the resolution times 10 to get the accuracy they're reporting. I don't know, maybe.
Okay, maybe. Yes.
Yeah.
Also, one of uh, let's say one of the things that missing in the paper is a mathematical framework of this project.
Yeah.
So it's
Yeah.
describes the concept,
Yeah.
but it doesn't describe all the maths and algorithmics behind it.
Yeah. Yeah. They probably do interpolation. It's not described. Which one? I don't know. They refer to paper 29. We describe this localization in high level and refers reader to 29 for more details. Now, I looked at 29. 29 is kind of the same idea, but in 60 gigahertz, and it's not the same authors. So uh, I don't know if they use the same math that they describe in 29 or not, but it's not this well described here. That's true.
Hmm. Right.
Yeah. All right. And any other stuff? But it's a nice idea, right, Alex?
Yeah, yeah,
What's
it's very nice idea, and you don't have to use it only indoor. You can also use it outdoor.
Yes, one
Uh,
hundred percent. They say. By the way, what do you think is the SNR they're getting here? Because they get a lot of clutter probably also for movement of the drone. The drone is vibrating all the time, right? And they probably get a lot of clutter near zero Doppler, and they completely ignore it because they have a nice return from the transponder from the anchor,
yeah,
right?
you must keep it high. You must keep the return from Anchor high enough so the range is limited. Otherwise, you will not be able to distinguish between cloud return and anchor return.
Right.
But it's not described here.
Right. Also, the fact that there is an anchor is also 1 over r squared instead of 1 over r to the 4, and that's also a
Yes,
nice gain, or 6 dB in SNR.
yes.
Uh, yeah, also, what about the Doppler? Right, it's not mentioned here, but the drone is moving, so I suspect, unless it's very fast chirps, I don't know how this radar works, but unless it's a strain of fast chirps, there will be some shift because of the Doppler here. No.
They mentioned in one of the papers
Hmm.
that the Doppler movement can affect the accuracy of the positioning, but it's
Hmm.
about several centimes,
Gotcha.
not more than that. They don't use they don't detect Doppler because the drone can be very slow.
Yeah, 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 yeah. I also see. I also seen in the demo that they move the drone very slow.
Yeah,
Um,
if you work indoors, you you must move it
yeah,
slow.
yeah. It must move slow. By the way, what are the from your experience? What are the applications of this kind of a concept?
I see some commercial applications like warehouses and
Hmm.
moving things from one point to other point. Uh, that's what I can think of.
Hmm.
Maybe you have other ideas.
Yeah. What about, let's say, I'm just thinking out loud, putting because, for example, firefighter, they go into a fire, they can't see anything because of
Mm-hmm,
the smoke. So
mm-hmm.
sometimes they will just do this, with the hands. And the commander, the one that is supervising everyone, the chief or whatever they're called, um, they want to know which firefighter where he is inside the building. Let's say, do you think it will work? Um, in terms of, let's say, you put a sensor or a radar transmitting, and you put an anchor at the other side of the building, and it goes through the walls.
Uh, it depends on the walls because here the 24 gigahertz frequency is not
Yeah, I
such a
know.
good for penetrating, and
Yeah.
also it's not ultra wideband technology.
Right.
So
Right.
if
Right.
you switch to lower frequency and maybe use ultra wideband technology, uh, so it could work.
Yeah.
It
Yeah,
could
I
work.
meant in general. I didn't mean specifically 24. But what is so special about UWB or ultra wideband that is making it go through obstacles more,
It's a
other than
good
the frequency? Sorry.
It's a good question because I worked with ultra wideband technology, and
Hmm.
it's actually much better than narrowband in penetration. And
Hmm.
I have many books in about and papers about ultra wideband, and all of them describe that they are much better than in penetration, but no one explains the physical effect. So I don't know the answer. I can think that the wall is much like a filter, and when you have and you don't know the parameters of this filter, but when you have quite large bandwidth, so something goes through. That's my
Hmm. Got it. Yeah. Yeah. Yeah.
explanation, but maybe I'm wrong.
Yeah. That's what I was thinking. But you're right. I didn't see the actual physical explanation for that, except for the low low frequency, higher wavelength. Um, Yeah. Okay, great. Great. Alex, thank you. Thank you for
Thank you, Nir. Thank you
doing
for
this
hosting.
presentation. Absolutely. And thank you for presenting it, and have a good day there in Israel.
Yeah, and you have a good night in California.
Thank you. Thank you very much. Bye,
Goodbye.
Alex. Bye bye. Bye.
Bye bye.
Bye. Bye, Alex.
Bye, Nir.